a particular long wavelength limit in which the equations of gravity in 5 dimensions reduced to the equations of hydrodynamics in 4 dimensions. Okay? And the full nonlinear limit. Is this situation correct? It is, as I've now been explaining. I've already explained to you, I've already shown you the metric for these black branes. Now, black branes represent stuff that's thermally equilibrated. Okay? If you want to make stuff just locally thermally equilibrated, that's a natural case. What you might want to do is take the parameters of equilibration, namely the temperature that appears in this metric, and the velocity that appears in this metric, and just make everything a function of space and time. That sounds like it should represent local thermal equilibrium. Okay? If I did it in this form of the metric, no, it doesn't work. Okay? There are many ways to see why it doesn't work, but perhaps the most physical is through a causal diagram. If you look at the Penrose diagram of ADS space, just linearized around equilibrium, this is the event horizon, this is the boundary. And making things a function of position, making things a function of position in this way basically tells you that what you're doing is using the values of temperature and velocity at the boundary to determine what happens in the bulk along these red tubes. Because these are lines of constant t in Schwarzschild type coordinates. T is lines of constant x mu in Schwarzschild coordinates. Suppose you took, see what we've done here is to keep x mu fixed. So at any given x mu as a function of r, have the whole metric determined by the velocity and temperature at that. Okay? What that's doing in pictures is determining the metric along this red line in terms of what's happening on the boundary here. Okay? But this makes no sense because, if I take the boundary and I hit it here, the response to that should be causal. Whereas these red lines bend backwards in a completely acausal way. This is clearly a stupid thing. What we should be doing is something like this, making our tubes along these blue structures. And there's a very elegant way to do that in formulas. The way of doing that is by first switching to what are called ingoing Eddington-Finkelstein coordinates for just the uniform black brane, and then doing this local trick. If you do that, what you're doing is foliating space-time with tubes that go along ingoing null geodesics. Okay? When you try this idea, everything falls into place. And this metric here is a legitimate starting point for a perturbative expansion of solutions to Einstein's equations in a derivative expansion. Yes?
Why did we switch to the causal line to the other one?
Well, for many reasons. Firstly, physically. You see, on physical grounds, you expect that, let's say you've got hydrodynamics, you've got some source, you bang it. The response in hydrodynamics will be causal. That should be causal also in the bulk. Whereas the red tubes will give you a causal response. Okay? So, that's physically, there were several technical reasons, which I won't try to explain. Okay. So, now we're working with this and taking this to be a starting point for a derivative expansion, or a solution to Einstein's equations in a derivative expansion. What does that mean? It means that we start with a metric, which at leading order is the ansatz that I wrote down here. And then I allow it to be corrected by corrections, which are weighted by numbers of derivatives. This epsilon is a counting parameter that counts how many derivatives you have. Okay? Now, you take this expansion, you plug it into Einstein's equations. The details, okay, let me tell you what happens. Order by order in derivative expansion, it turns out you can just solve this perturbative problem. What do I mean? I mean, you can determine the first correction, then the second correction, then the third correction that will take what was a solution of Einstein's equations at zeroth order in the derivative expansion, make it a solution of Einstein's equations to first order, or second order, third order in the derivative. More precisely, you can solve what I call the dynamical Einstein equations. What I call the dynamical Einstein equations to each order. However, what you're left with is a problem of solving the constraint Einstein equations. Now, Einstein's equations have this property that if you solve the dynamical equations everywhere, then you don't need to solve the constraint equations everywhere. You only need to solve them on one slice. Okay? So, it turns out that the structure of the constraint equations, if you just take that one slice, because of that, these constraint equations are effectively not functions of R, because you can study them at your favorite value of R. So, the constraint equations are equations in 4 other value dimensions. Okay? And the structure of the constraint equations is simply the conservation of a tensor, which, in fact, according to the ADS-CFT correspondence, has the physical interpretation of stress tensor of the field theory, where that tensor is not something arbitrary, but is determined to be a given functional of the velocity and temperature fields of the that you started your expansion with. Okay? So this functional is built by solving the dynamical equations order by order by order. And then you have to ensure conservation of this function. So in other words, what you get is the equations of hydrodynamics. Because you get that you've got a solution of Einstein's equations provided your stress tensor is conserved when the stress tensor is made out of a particular functional of temperature and velocities. Now you have no freedom in this case. Einstein's equations determine your constitutive relationship for you. You just read them off from this equation. This is explicit to second order, but you can continue this equation, this procedure to 13th order if you want. Okay? So let me say that again. For every u, mu, and t that satisfies the fluid dynamical equation del u, t, mu, nu is equal to 0, we have a solution to Einstein's equations. Moreover, the map from long wavelength gravity to hydrodynamics is 1-to-1 in the following sense. Suppose we are given a gravity solution that is due to a particular solution of hydrodynamics. Then you look at any nearby gravity solution that is also wavelength, long wavelength. That will be given to a nearby solution of hydrodynamics. So it's a perfect equivalence of two dynamical systems. With the one restriction that you have to restrict yourself to the gravity side till you only have long wavelength modes, fluctuations, and only have regular solutions in a manner that I haven't had time to explain. Okay. Great. So, the solutions that we deal with are singular at R equals 0. This is the nature of all black hole solutions. All black hole solutions are singular. That doesn't worry us usually because the singularity is shielded from the outside by an event horizon. Quite remarkably, in the context that I'm talking about, it's possible to actually show that these solutions have an event horizon and to compute the event horizon benefit. Okay? This computation gives us practical benefit. This is a response to one of your questions. You see, it's a classic theorem of general relativity that little bits of the event horizon area always increase in time. That theorem can be pulled back from the event horizon of our solutions to the boundary to produce an entropy current, which you can show is always positive divergence. Namely, locally, entropy in these solutions is always produced and never destroyed. And so this just follows from the Hawking area increase theorem. We'll come back to area entropy increase as well. Okay, so this just from this point of view is an output, not an input. Okay. I've gotten it wrong way. Okay, excellent. I'm now going to talk about a small generalization. The main idea of the map between fluid dynamics and gravity is done. Any questions about it? Great. Okay, everything I said can now be generalized to charge fields. The generalization is very simple. On the bulk side, in addition to studying Einstein's equations, you need to couple Einstein's equations to Maxwell's equations. On the boundary side, as we explained, in addition to stress tensor, we have charge field. Okay, but the basic idea just goes through. Now, when you first try to work this out, it looks like it's going to be a routine extension of what you get. However, when you work things out in detail, it turns out that there is a term in the charge current proportional to epsilon mu nu rho sigma, omega nu rho u sigma. Omega is the vorticity. This looks fine. It respects all symmetries of the problem, but there was a problem that was pointed out to us by Taxon. And the problem was that if you open the textbook of Landau-Lifshitz, which claims to have classified the most general first-order equations of hydrodynamics, yes, this term does not appear. Yes.
The duality is between quantum field theory and classical
gravity.
Where is the quantum here?
You see, it doesn't matter how quantum the field theory is, the hydrodynamics is classical.
Yes.
So it's the hydrodynamics.
Gravitation also is. The gravitational field is also classical.
Yes.
It's
So
both classical.
they're both classical.
So, but the duality is between quantum field theory and.
Exactly.
So,
However, even quantum field theory has an effectively classical hydrodynamic description. So the duality was between quantum field theory and classical gravity. But quantum field theory in a particular limit reduces to classical theory, namely classical hydrodynamics. So therefore you get, there should be a map between classical hydrodynamics and classical gravity. So then this is very easy now. It's just a map between differential equations. Is this clear?
so you don't have to go through.
No quantum. This is the great thing.
Okay.
Just anyone can. Okay. Great. Other questions or comments? Okay, so we were talking about this term. This term in the constitutive relation. This term was a term that was not present in standard listings of allowed terms in the constitutive relation. And the first communications we got from the experts on the subject was that your paper looks very interesting, but it can't be right because you compare with Landau-Lifshitz, the terms are not there, so it can't be right. Okay, this has a long history. Don't know Landau-Lifshitz were wrong is a hard word, incomplete. Okay, I now want to explain why. How did the Landau-Lifshitz constitutive relations come about? Because Landau-Lifshitz worked in a derivative expansion, imposing constraints on symmetry like we talked about at the beginning. In the case of charge relativistic hydrodynamics at first order, as I explained at the beginning, you get 7 structures. This is too much on every reasonable physical ground. And the equations listed in Landau-Lifshitz didn't have 7 parameters, but 3 parameters. How did they cut 7 down to 3? They cut down using very reasonable physical reasoning. The cut down from 7 to 3 in Landau-Lifshitz was from the requirement that they imposed on physical grounds that the equations of hydrodynamics are compatible with the existence of an entropy current whose divergence is positive at every point in the fluid flow. That requirement plus an obvious, for them, obvious statement about what the entropy current was, gave them a 3-parameter set of equations of hydrodynamics that did not have that term that we talked about. Okay? However, from what I told you already, if we haven't made a mistake, this can't be right. Because we found equations of hydrodynamics that manifestly have a positive divergence entropy current from Hawking areas in the field, and has this term that Landau-Lifshitz don't have. So how does this work out? It was a long story. It's cleared up eventually by Sohn and Soroka and many other people. The problem was that it turns out that the Landau-Lifshitz guess for the form of the entropy current was not always correct. You know, they guessed at first order that the entropy current would be S times U. Okay, you could have more. Please.
Can you be explicit? Like what?
Like what? I may have the formulas here, but things involving epsilons and omegas. I don't have the formulas here, but I could show you.
So you break something with this.
You break parity, for instance.
Very good.
Yes. Yeah. So if you preserve parity, this is all that you could have. However, the field theory that we were looking at does not preserve. Okay, understand it? Yes. Yeah, things involving vorticity. Okay. The fact that such a term is allowed in the equation of hydrodynamics is unexpected and we'll now turn to explain it. Okay. You can understand this in 2 different ways. Okay. So, one way of trying to understand this is just to use the same logic that Landau-Lifshitz employed. Okay? But do it correctly. That is, make no a priori assumption about the structure of the entropy current beyond those imposed by symmetries. Okay? And self-consistently find all solutions to this criteria. Okay? When you do it correctly, it's very, very constrained. In particular, if you assume parity invariance, you get the same three parameters that Landau-Lifshitz had. However, if you do not assume parity invariance, and in particular account for the effects of some global anomalies, as I briefly tried to indicate, not only is the set of the three parameter set that lambda evolutions we're looking at, not only is that incomplete, it cannot be the right answer. Okay, I'm going to try to explain some of this. Okay, so this, if you just implement their procedure correctly, you come to this conclusion. However, I'm going to explain this to you from another point of view that's actually simple. Okay, and the other point of view is to switch from their way of thinking to imposing another physical constraint of fluid on a long distance field theory. And the other physical constraint is this. Consider a field theory now not in flat spacetime, but consider it on this time independent manifold. Okay, ds squared is equal to this stuff. So gij is any function of x. AI is a cross term, like Kaluza-Klein gauge field between dt and dxi. The important thing is that none of these fields are functions of x. So this is stationary configuration. Okay? Now, and you can also allow stationary gauge field. Now, because this is stationary configuration, energy is conserved. The energy is conserved in this theory. And so the partition function of this theory, trace e to the power minus beta h, along with some chemical potential business, is well defined with able to conserve charges. Okay? Question, what is the answer to this partition function as a functional of the background metric fields and gauge fields? Okay? The first thing to know, of course, in general the answer is going to be very complicated. But the interesting thing to note is that in the long wavelength expansion, you expect a local answer expanded in derivatives. So the question that you ask is, what can you say about the structure of this partition function in an expansion in derivatives? For a charged fluid at first order, where we have this mismatch with lambda Lipschitz, if you work it out, is just from consideration of index structure and invariances. Okay? The only thing that you could write down to first order in the derivative expansion is this. At first order, at zeroth order, you just have the integral over some density function. And if you think about it, the density function should be identified with the pressure of your system as a function of a local temperature, which is given by T naught times e to the power minus sigma, and local chemical potential is given by this quantity. There are the only possible first order allowed corrections to this thing at first order all involve interesting structures. Structures that know about the fact that we were working with a four-dimensional theory. Namely, they involve integrals of Chern-Simons forms over the three-manifold. That is the manifold that you're integrating your field theory of, removing time. Okay? Now, these Chern-Simons structures here are of three types. There's gauge field with gauge field, Kaluza-Klein field with Kaluza-Klein field, and gauge field with Kaluza-Klein field. And in addition, if your U1 theory, U1 symmetry of your theory had a U1 cube anomaly, we've written down here the most general gauge invariant action. But you should have a piece here that captures the anomalies. And such a piece here would capture the anomaly with a particular anomaly coefficient C. So this is the most general structure of your partition. Now, if you think about it for a minute, you will see that two of these terms here have to be zero, just by from CPT invariance. This term and this term have to vanish. Okay? Two terms are allowed to survive. This one completely controlled by the gauge anomaly, and this one which at first sight seems to be free. A very clever argument by Amos and collaborators actually connected this term here to another anomaly. They have a mixed gauge gravity anomaly. Okay? So this partition function here is completely determined to first order the derivative, the first correction of the partition function, first order derivative expansion, completely determined by two anomaly coefficients, which is very interesting because they compute in anything. Okay. Now, what has this partition function got to do with hydrodynamics? The basic idea is very simple. See, in any time-independent configuration, the field theory should equilibrate. Within the theory of hydrodynamics, equilibration means there must exist a stationary solution of hydrodynamics on that manifold. Okay? And then everything that we got from the partition function, from here you can compute the stress tensor and charge current in equilibrium by varying this partition function with respect to metrics. Right? Everything that you get from the partition function should also come out of that equation, those equations of hydrodynamics. But the answer to what your stress tensor equilibrium and gauge field in charge constant equilibrium will depend on the constitutive relations of hydrodynamics. So the fact that you reproduce this partition function, or the stress tensor and charge constant from this partition function, from the equation of hydrodynamics, constrains the equation of hydrodynamics in an important way. Note, by the way, that C0 and C and C2 are just pure numbers, which are not in any way. So it's a strong constraint on the first order constitutive relations of hydrodynamics. And if you work out what that constraint is, it gives you the same three parameter parametrization of the 7 coefficients that you got by correctly implementing Landau's physical constraint. Okay? The same thing that would give you Landau's answer if you set parity, if you set the anomaly coefficients to 0. But when the anomaly coefficients are not 0, and as they're not in the standard model, you get differences. Okay. It's interesting that two apparently different principles, namely the principle of entropy increase, local entropy increase, the principle that equilibrium should always exist, give the same answer for constitutive relations. In fact, Shantini Bhattacharya has shown that this agreement persists to all orders. More specifically, she has shown that if you implement the constraints from the existence of a partition function, and add to that just 2 additional constraints, namely the viscosities are positive and the conductivity is positive, then for such a fluid you can always produce pointwise increasing entropy current. I find this result very interesting, because it comes near within the framework of hydrodynamics to a proof of the second law of thermodynamics, which was supposed to be something deep. Right. Okay, very quickly, a few other things. Okay, we have a time? No. 5 minutes? Yes, okay, great. Now, let's look at some generalizations. A partition function in quantum field theory is a path integral in Euclidean space over a thermal circle whose circumference is of length 1 by t. Now, there is a natural and very interesting and very useful generalization of such a path integral. You look at a path integral that goes over the imaginary time axis,